Right, hi there, guys. So welcome to the second video of this series of revision videos to help you basically prepare for your Year 11 exams. Today's topic is going to be atomic structure. So this is the chemistry version of the atomic structure, because there is also a physics topic called atomic structure too. So what I'm going to do is, as if you've been watching, well, if you've watched the previous video that Mr. Gilbert put out, I'm going to be using an exam question to help you kind of decode it, deconstruct it, but really more importantly, bring in the revision topics, the ideas that you need to know in order to answer any question that covers the themes that this one does. And obviously, you can download and grab a copy of the questions and the answers that I've got in front of me here so that you can work along side the video. So if you haven't already done that, if you can get the questions up yourself on a screen, or better yet, print it out if that's possible, then you'll be able to work alongside me. If not, work along through the questions and then watch this video as a backup to help you understand any points that you've missed. Okay, so the overall theme of atomic structure, so that's C1, some people like to think of it as C1, the first chemistry topic, is exactly that, the structure of the atom, the history of the atom, but also linking that then to the periodic table and the development of the periodic table itself. So this first question that we're going to take a look at looks at the former, looks at the structure and the model of the atom, and kind of some of the developmental changes that it's been through. But then I've also chosen this one particularly because of some of the maths that it contains, because we can't forget that your science GCSEs comprise of a big chunk of questions that will involve maths. So we'll get onto those parts as we start to work our way through it. So let's start here with the first part of the question, question 1, part A. So we've got here two pictures within figure 1 that show models of the atom, and you can see that they look quite different. You can see on the left-hand side, we've got the plum pudding model. And on the right-hand side, we've got the nuclear model. Now, these models have been proposed by different scientists. So the plum pudding model was proposed by a scientist called J.J. Thomson. And the nuclear model was then a developed version that was proposed later on by a scientist called Niels Bohr. So we'll cover some of this in some more detail later on in the video. But these are just two models of an atom based on the knowledge at the time. Okay, so in terms of the question, what we need to do is label these diagrams. So it says label the diagrams, obviously in figure 1, using answers from the box. So if we take a look at the plum pudding model first, the plum pudding model proposed that there was an overall atom that was positively charged, and within this atom, there were embedded areas of negative charges that were called electrons. So you can see that this circle here with the negative sign in there, that's going to be our electron. Now, at this point in time, scientists didn't know of the existence of protons. So instead, that they thought that the electrons were embedded within an overall positively charged blob, if you like, okay? And that was simply the atom. So this overall larger circle in the background is the positively charged atom. As that model developed, and then through a series of discoveries and increase in knowledge, developed the nuclear model, you can see that the model's changed slightly now, in that we've still got the electrons moving around the nucleus, but we now know that they are in particular orbits. So that's what this label here that's specifically pointing to the black line is referring to. So this is an orbit. This was proposed by Niels Bohr, that the electrons are circling the center of the atom itself, which is referred to as the nucleus. But even at this point, Niels Bohr had no idea what was within the nucleus. So within the nucleus itself, we were yet to discover, which we obviously now know are the protons and the neutrons. Okay, so that concludes part A. Let's move on to part B. Explain why the total positive charge in every atom of an element is always the same. Well, first of all, let's think about where the positive charge comes from. So the positive charge of the nucleus of an atom is provided by protons. So positive charge provided by protons. So they are the subatomic structures that are actually contributing the positive charge of the atom. Question does state, though, state why the positive charge in every atom of an element is always the same. So the same, well, if the positive charge is provided by the protons, then the positive charge of an element must always be the same because it contains the same number of protons. So every atom of a particular element contains the same number of protons. So for example, all lithium atoms contain 3 protons. So each proton contributes 1 positive charge. So having 3 protons means it's got a charge of 3+ in its nucleus. So it contains the same number of protons. Okay, and we can find out what that number is by looking at the periodic table and paying particular attention to the atomic number of an element. The atomic number tells you how many protons a particular atom of a type of element has. So if I just use the whiteboard here, if, for example, if we just keep focusing on lithium for a second, what we'll see on the periodic table is that we obviously see the symbol Li. We see a mass number of 7, which is exactly that, the mass number. This tells you how many subatomic structures there are in the nucleus. And then at the bottom, we'll see the number 3, which is the atomic number, and tells us that lithium atoms have 3 protons, and therefore the nucleus of a lithium atom will have a charge of +3. Okay, moving on to part C. So this is the first of the maths element of this question. So it states here that the results from the alpha particle scattering experiment led to the nuclear model. Alpha particles were fired at a thin film of gold at a speed of 7% of the speed of light. Determine the speed of the alpha particles. So this refers to an experiment done by Rutherford and Marston, and they, like the question states, fired alpha particles at a really, really thin piece of gold and observed what happened to those alpha particles in terms of whether they were able to get through, whether they were deflected, whether they bounced back. Now, the question is focused solely on the maths. So we've got the speed of light here. We're told that the alpha particles were fired at 7% of the speed of light. So we need to find out what that speed was of the alpha particles. Well, essentially what we need to do is apply the 7% to the speed of light, because we're told that the speed of the alpha particles was 7% of the speed of light. Well, 7% as a decimal would be 7/100, which gives us 0.07. So to apply this percentage to that, what we simply now have to do is multiply 0.07 by 300 million, which is the speed of light in meters per second, and see what we get. So 0.07 multiplied by 300 million. The answer is going to be in meters per second, as is written here at the bottom of the question. And we're also given the speed in meters per second. So there's no need to convert that. All we need to do is multiply those two together. So 0.07 times 300 million. And we get here 21 million. So 21 million meters per second. Or if you wanted to, you could state that as 2.1 times 10 to the 7 in standard form. But there's no requirement to do that. It doesn't tell you to do that. So you can leave your answer as 21 million meters per second. Okay, great. Moving on to the next part of the question, which again is another maths question. So what we've got here is in part D, figure 2 showing two atoms that are being represented as solid spheres. So this is just a representation of these atoms. We've got a hydrogen atom here, which is the lightest, smallest element. And we've got a magnesium atom here. And essentially, these diagrams are showing the relative sizes. So the sizes compared to each other. We're told here that a hydrogen atom has a radius of 2.5 times 10 to the minus 11 meters. So incredibly small radius. What we need to do is use this very important bit of information to then determine the radius of a magnesium atom, because this is the radius of a hydrogen atom, which is the distance from the center to the outside. And we need to use this diagram to help us work out the radius of a magnesium atom. It tells us specifically to use measurements from figure 2. You're only going to be able to get the answer to this question if you use measurements from figure 2. So what do? Well, we've got two circles here that are representing the spherical atoms, and we know that these are relative to each other. Okay, so the easiest thing for us to do is to find out, well, how many times bigger is this magnesium atom compared to the hydrogen atom? We can find a ratio. We can do that by, first of all, measuring the diameter. So that's just the distance across. You could do the radius, but it's probably easy to do the diameter, because you don't then have to estimate where the middle of the atom is to basically work out the distance between that point and this point there. So the other side of this circle. And I'm reading that on this particular photocopy as 12 millimeters. Okay, so this has a diameter of 12 millimeters. So what I now have is, what I've now got to do is work out the diameter of the magnesium atom. So if I take my ruler and get it slap bang in the middle like that and measure the distance from there to there, what I can see is it's got a diameter of 75 millimeters. Okay, right. So now what I need to do is find out how many times bigger that diameter is compared to the diameter of a hydrogen atom. So simple calculation, 75 divided by 12. Into my calculator. So how many 12s go into 75? 75 divided by 12, and we get an answer of 6.25. So essentially that magnesium atom is 6.25 times bigger than the hydrogen atom. So because we know the radius of the hydrogen atom, we can simply multiply this now by our ratio, which is 6.25. So we're going to multiply this by the diameter of the hydrogen atom, 2.5 times 10 to the minus 11 multiplied by 6.25. So what we get, still got that on my calculator. It's just going to multiply that by 2.5 times 10 to the minus, don't forget the minus 11, and we get 1.5625 times 10 to the minus 10. What we'll do is we'll round that to two decimal places. So 1.56 times 10 to the minus 10 meters. So a little bit of simple arithmetic there, a little bit of simple kind of problem solving. Okay, remember to use the question, the clues in the question, to help you figure out what it is that you need to do. Okay, so again, maths quite important when it comes to particularly chemistry and physics, but your GCSE science in general. Okay, right, question 2 then. So it's the second and final question that we'll take a look at to give us an insight into atomic structure. And this one focuses on the periodic table. So the two elements of atomic structure are the atom and the periodic table. Okay, so let's read the question through. This question is about atoms and chemical elements. Mendeleev's periodic table has groups of elements with similar properties. Figure 1 shows part of Mendeleev's periodic table. So you see it looks really different to periodic tables that you're used to. Is it's a little bit more primitive. It's one of the early attempts that Dmitry Mendeleev did to put all of the known elements at the time into their rightful places. So compare Mendeleev's periodic table with the modern periodic table. Just give me a second to grab a periodic table, and here we go. See, looks really, really different. Okay, this is the modern periodic table, full of elements, has a very characteristic shape, and this is the early one. Remember, you'll have a copy of this in the exam, albeit not yellow, but you will have a copy. So an instruction like compare Mendeleev's periodic table to the modern periodic table isn't just asking you to, well, try to just picture that in your mind's eye. It's literally going to be there on your table. You're going to find that on your table, so make sure you use it. Which group is missing from Mendeleev's periodic table? Well, if we compare the two, take a look at this side here. Hydrogen, lithium, sodium, potassium. We see those on this particular periodic table here. Albeit we see hydrogen there, we see lithium, sodium, potassium. Then in the second column, the second group, beryllium, magnesium, calcium. Beryllium, magnesium, calcium. So group 1 and 2 are definitely present. If we switch over to the other side, this final full column, fluorine, chlorine, manganese, chlorine, chlorine. We don't see manganese, but we see bromine. But we can still see that the seventh group, which is group 7 on this periodic table, is present. And what we won't see on Mendeleev's early periodic table is any of the group 0 elements: helium, neon, argon, krypton, xenon, radon. Definitely not argonescent. And the reason for that is that those hadn't been discovered at that point. Group 0 elements had not been discovered. They're inert, they're unreactive, they're essentially invisible. Well, they were at the time anyway, because of the primitive tools and devices and basically scientific techniques that were available at the time. So the answer to that question is group 0. Okay, so once again, although we need to rely on memory and facts that we've learned, sometimes we have the answers on our tables staring at us. So question B. In the early periodic table, some elements were placed in the wrong groups, as we can see here, manganese, for example. Mendeleev overcame some of these problems in his periodic tables. Give 2 ways Mendeleev did this. Well, once again, we've got the answers in front of us. What you should have noticed looking at this particular periodic table is we have a box here for an element. We don't actually have a symbol in there. So one of the key things that Mendeleev did is he realized that there were elements that were yet to be discovered. So this element here, titanium, most other scientists would have plunked it there. But because titanium doesn't fit the pattern, if you put titanium there, it doesn't fit the pattern above it with the other elements in the periodic table. It doesn't necessarily make sense to put it there because there's going to be something else that we haven't discovered that fits the pattern of reactivity that Mendeleev was certain was the reason why you place elements in particular positions. So first and foremost, Mendeleev left gaps in the periodic table for elements that were yet to be discovered. Really, really important. Genius at the end of the day to think that way at the time. The second one. In some places, scientists had placed elements in particular orders, and they hadn't really paid attention to the weights, the atomic masses. As you can see in this periodic table, the masses all increase. So 7 to 9.4 to 11, 12, 14, 16, 19. In every position, we've got the atomic masses increasing. So that was Mendeleev's second really important idea, to put the order according to the atomic masses. So order in terms of atomic mass. So we know now that actually we've come on a little bit from then in terms of ordering the elements in the periodic table. If you look at the modern periodic table, you'll actually see some areas where the elements aren't actually in order of atomic mass. You've got here antimony with a mass of 122, tellurium with a mass of 128, and then iodine, whose mass is actually lower than tellurium at 127. So even since Mendeleev's time, the periodic table has been developing, and you can see now instead we order the elements according to their atomic numbers. So just using that neck of the woods in the periodic table, 49, 50, 51, 52, 53. So we can see the atomic numbers go up by 1 each time. Okay, moving on to the last section of this question. To continue with the theme of the important scientists involved in the periodic table, and more so in this question in terms of the atom itself. We've got here a question that wants us to draw a line from each of the scientists to the key discovery made by that scientist. Now, you need to know a number of scientists in order according to their contributions. And when it comes to the atom, we start with John Dalton. John Dalton, J.J. Thomson, Rutherford and Marston, Niels Bohr, and then finally James Chadwick. Now, Niels Bohr in particular is famous for essentially coming up with the idea that the nucleus of the atom is at the center and that it's orbited by electrons. So in this particular question, it's straight across. Okay, so Niels Bohr, electrons orbiting the nucleus. Now, James Chadwick, remember it says draw one line, so make sure you read the question carefully, one line, not multiple lines. James Chadwick, his main contribution was discovering the neutron. So he's almost last in this list of scientists that starts with John Dalton. For anyone who wants to go back and check the scientists involved, make sure you open up that atomic structure booklet from year 9, because that's when you did it. And then you can refamiliarize yourself with all the different scientists involved. So James Chadwick, existence of neutrons. Okay. Next part of the question focuses mainly on the subatomic particles. So subatomic particles include, as this says, electrons, neutrons, and protons. And in this particular question, a beam of these 3 subatomic particles, it states, can be separated. And that's because each of these subatomic particles has different properties. We know, for example, that electrons are negatively charged. We know that neutrons have no charge, so are essentially 0 in terms of charge. And we know that protons are positively charged. So because they have these 3 unique characteristics, we can use those characteristics to separate them. And it says here that they can be separated by passing them through an electric field. So the electric field in this question, in this example, is set up by placing 2 charged plates, positive and negative charged plates. There is an electric field between these 2 plates. Now, the beam of electrons, neutrons, and protons is being fired through the field, through the gap between the charged plates. And the diagram shows us the direction of the 3 particles after they enter the electric field. If we take a look at the directions that the 3 particles take, you've got one that zooms off this way. You've got one that carries on going straight, almost unaffected by the electric charge. And you've got one that zooms off this way. So let's take a look at direction A first of all. Well, why would a particle deflect at a really large angle this way? So you've got a positive charge here, a positive plate here. So it's almost as if it's attracted to that. But at the same time, it's being repelled by the negative plate. So what would repel a negative plate but attract a positive plate? Well, it will be something that is negatively charged, because something that's negatively charged would attract a positive charge but repel a negative charge. So direction A has got to be the electron. What about direction B? Well, direction B, the object that's taken direction B is straight through, unaffected, not bothered about positive or negative charges. Well, if we take a look at what we talked about first, neutrons are neutral, so they're not going to be affected by positive or negative charges. So direction B has got to be the neutrons' direction. Okay? Right. Lastly, obviously, by the process of elimination, we can deduce that the proton must have moved in the direction of direction C. But just so we can discuss that, make sure we're all on the same page. When it comes to the reason, protons are positively charged. They're obviously going to repel other positive charges, and they're going to be attracted to negative charges. So off we go in this direction if we're a proton. So direction C is a proton. One more thing, just in the kind of like the spirit of stretching and kind of like going into a bit more detail. You take a look at the electron's direction, it's much more obvious. It's changing direction much more, whereas the proton's almost lumbering to change direction. It doesn't change direction at such a large angle. And that's due to the fact that protons are quite big in terms of mass. They are big, whereas electrons are tiny, absolutely tiny, which means that something that's quite small is going to be influenced because its mass is quite small, much more greatly by an electric field. Whereas a proton, because of its size, it has a bit more momentum. So just like, a larger object moving, trying to change its direction is not as easy. So it doesn't change direction by such a large angle. It's just something to think about, just to kind of stretch yourself. Okay, on to the last section. Got a question here. Calculate the mass of one atom of sodium, and it gives you an equation to use. Now, it might not necessarily be an equation that you've come across in lessons, but it's an equation that's literally there in black and white nonetheless. So calculate the mass of one atom of sodium, and it tells you that the mass of one atom of sodium equals the relative atomic mass divided by the Avogadro constant. We're given the Avogadro constant as well, which is 6.02 times 10 to the 23, which is an important value and definitely one that you'll come across when you're revising the quantitative chemistry section. Okay. It also asks you to give your answer two significant figures. So let's start putting the numbers into the formula. So in order to work out the mass, we need to know the relative atomic mass of sodium. So for that, we need to refer to our periodic table. Sodium is found in group 1, right here on the left. Its relative atomic mass, or its mass number, is the big number at the top, which is 23. So in terms of this equation, the top number is 23. We're going to divide that by the Avogadro constant, which we're given. So 23 divided by 6.02 times 10 to the 23. So let's plug those numbers into the calculator. 23 divided by 6.02 times 10 to the 23. Of course, we get this really, really big number. Okay, well, it's a big number in terms of the number of numbers that are on my screen. It's actually a really tiny number because, as you can see here, it's actually to the power minus 23. But if we just write down that answer, so 3.8205, that'll do, times 10 to the minus 23, then we're almost there. The reason why I say we're almost there is because we're asked to give our answer to two significant figures. So to two significant figures, this answer will be 3.8 times 10 to the minus 23. So remember, two significant figures doesn't mean two decimal places. It means two significant figures. So there's our first significant figure, 3, and there's our second significant figure, 8. So the answer is 3.8 times 10 to the minus 23, which is an absolutely tiny mass, which makes sense. It's one single atom of sodium. So really, really tiny. So remember, in some questions, you're not being asked to remember this formula, but it's there and you've got to be able to use it. And you've also then got to stick to the commands of the question, which are in terms of giving your answer to a certain number of significant figures. If you don't do that, you're not going to get 3 marks. You're only going to get 2 marks if you leave it at that. Okay? Right, finally, last question of the lot. The radius of a sodium atom is 227 picometers, so a phenomenally small number. We're also told that 1 picometer is 10 to the minus 12 meters. So if you thinking of it in meters, it's absolutely tiny. This is an important piece of information. They wouldn't give you this piece of information unless they wanted you to use it in some way. So sodium atom has a radius of 227 picometers, where 1 picometer has 1 picometer is equivalent to 10 to the minus 12. So we could write the radius of a sodium atom as 227 times 10 to the minus 12 meters. Could write it like that rather than using picometers. We're almost converting it into meters by doing that. The radius of the nucleus is 1/10,000th of that atom. So you've got a sodium atom that is across the middle, across the middle to the halfway point, 227 times 10 to the minus 12 meters. And at the middle, you've got a nucleus that is 1/10,000th of that width. It says here, which calculation shows the radius of a sodium atom's nucleus? Well, think about it. If the radius is 2, and I'm writing this out now for the third time, 227 times 10 to the minus 12 meters, and the nucleus at the middle is 1/10,000th of that, well, to work out its size, you could simply just multiply by 1/10,000th. Which, if you take a look at these answers, is actually present right here at the bottom. 227 times 10 to the minus 12 times 1/10,000th. So that is our answer. Okay, so there's no substitute really. And we've been talking about this during Parents' Evening, which if you're watching this video quite far down the line, probably don't remember. But it's definitely something we'll be mentioning over and over again in lessons. There's no substitute for revising, okay? Trying to do as many questions as you can, okay? Giving yourself kind of like that repertoire and that variety of questions by doing as many as you can. Because the more you do, the less chance there is that in the exam, you're going to be thrown by a question or a question style that you've never seen before. Okay, well, I hope you found this helpful. In terms of the next video, I believe it's on energy. So you can look forward to that in the next week or so. Okay, thank you very much. Thanks for watching. Bye-bye.